for multi-valued logic also we can go for parallel gate evaluation. So, if we take ternary logic as an example, and assuming that my my computer has got w bit wide word. Now, so V0, V1 and V unknown, suppose that is a 0, 1 and unknown. So, these are the three symbols that we have in the ternary logic. Suppose their corresponding codings are 0, 0, 1, 1 and 0, 1. So, what we do with each signal x, we have two words x1 and x2. x1 stores the first bits and x2 stores the second bits of the w copies of same signal. So, we have got this x having two words x1 and x2. Now, this AND OR operations, so they are implemented like this, the C equal to OR of AB. So, where C1 part is computed as OR of A1 and B1 and C2 part is computed as OR of A2 B2. Complement is reversed, like C1 is computed as NOT of A2 and C2 is computed as NOT of A1. So, it is like this, that suppose I have got say this one AND operation of 0 and 1. So, the result should be 1. So, what is happening is that 0 is represented by 2 bits 0 0 and this 1 is represented by 2 bits 1 1. Now, when I am doing the AND operation, so I have to produce. So, this is your say x and this is my y. Now, this so this is now when I am doing the AND of these two. So, this 0 and 1. So, these two will be ANDed and then it says that 0 and 1. So, these two bits will be ANDed and accordingly this will produce a 0. Similarly, this 0 and 1 they will be ANDed and it will produce a 0. So, result is 0 0, which is equivalent to the ternary logic 0. So, in ternary logic I am getting say 0 and 1, that is equal to 0. But in case of inversion, what happens is that this is suppose I have got some pattern, suppose I had 1. Okay, so, 1 is represented as 1 1. Now, when I am taking an inversion, so this, if you look into the rule, it says that C1 is not of A2 and C2 is not of A1. So, this is coming here. So, this is getting a 0 from here and this is getting a 0 from there. So, I am getting a 0 0. So, why is it done like this? Is because if one of them is u. So, u is so if the symbol is u, value is u. So, which is represented by the symbol like this 0 1. Now, when I take NOT over u, the result should also be equal to u. So, as per this rule, it says that for getting the NOT of this symbol, this one value, the second part, it should take the invert and take it here. So, in the first part we should take the invert and taking to this position. You see, by doing this I am getting the pattern 0 1, which is the representation of unknown. If I do it directly, then there is problem, because I will get 1 0 and 1 0 does not have any counterpart in the ternary logic representation that we are following here, the symbol encoding that we are following here. So, this AND OR operations, they can be realized by applying the same bitwise operations to both the words. Like if you are doing say OR of A and B, then it is basically OR of A1 B1, C1 equal to OR of A1 B1, C2 equal to OR of A2 B2. Similarly, if we are trying to do AND, so C1 equal to AND of A1 B1, C2 equal to AND of A2 B2, and this one is. So, this way from this symbol is, if it is encoded like this, so we can take help of this multi-bit word of computer, the host computer, and do these operations in a single shot. There are several timing models that we need to consider. There are like transport delay, inertial delay, wired delay, functional delay. So, basically when I am doing this simulation, so this delay part also has to be modeled. So, there are several types of delays like this. Suppose the transport delay. So, transport delay is the time taken it takes for the effect of gate input changes to appear at the gate output. Suppose I have got a gate G like this, it has got a nominal delay of 2 nanosecond. That means, if A is equal to say B is permanently set to 1. So, B is not changing, only the value of A is changing. So, A was initially low and then A is becoming high, after one time unit it is again becoming low. So, if the nominal delay of this gate is 2 nanosecond, so from this event to come to F, so it takes 2 nanoseconds. So, I get the output becomes high at this point, and again there is an event on line A at this point. So, this will take another 2 nanosecond to propagate to the output. So, this takes another 2 nanosecond and comes down to 0 after this time. So, this is a nominal delay operation. Now, there may be rise and fall delays separately. So, the rise delay may be 2 nanosecond and fall delay may be 1.5 nanosecond. So, in that case what will happen when it is rising. So, this rising the rising effect or rising event to get reflected onto the output, it takes 2 nanosecond. This falling event, it takes 1.5 nanosecond to get reflected. So, it is like this. So, this can happen because of this logic families that we have. So, as a result we can have different types of this rising delay and falling delays may be different, they need not always be same. Also, there is another type of delay model which is known as min max delay. So, min max delay is there is a range of time that is specified, d min is 1 nanosecond and d max is 2 nanosecond. So, it says that suppose this value changes, so at this point, so the output will change between these two time, minimum it will take 1 nanosecond and maximum it will take 2 nanosecond. So, between that time the output will change. Okay. So, output has changed somewhere here. So, basically between 1 and 2 nanosecond it has changed. Similarly, when it has fallen here, the input A has fallen here. So, again between 1 and 2 nanosecond this has changed. So, it can happen anytime. So, it can happen immediately, or it can happen at the boundary, or it can happen in between. So, between d min and d max. So, this type of delay modeling, so they are known as transport delay modeling. Then there is something called inertial delay. So, it says that the minimum input pulse duration necessary for the output to switch states. So, it may so happen that d1 or di is 1.5 nanosecond. So, if I have got a pulse duration less than that, so then it will not be affected. So, here it is say di, this pulse duration is is 1 nanosecond, that is less than di, the inertial delay. So, this did not get affected onto the output. So, it continued like that. On the other hand, so pulse duration it may be greater than di. So, it is greater than di. So, it gets affected and it has got a nominal delay of 3 nanosecond, dn equal to 3 nanosecond. So, this effect comes to the output after 3 nanosecond. So, after 3 nanosecond we get a pulse of 2 nanosecond width, and then again this is falling down, and then that is more than 1.5 nanosecond it is remaining low. So, it gets reflected at the output. So, this is the inertial delay. So, the inertial delay is the amount of time that is needed, the minimum duration for which the input must be held at a particular value for the output to switch. Then we have got wire delay. So, wires are inherently resistive and capacitive. So, depending upon the range of frequency in which we are operating most of the digital circuits. So, we have got this resistive and capacitive effect coming into picture. So, we do not have inductive effect much until and unless we go to the RF frequency range. So, it takes a finite amount of time for the signal to propagate along the wire. So, this is the if I have got this line A feeding these 3 gates. Now, you see that there will be some delay associated with this individual segment. So, DAB, DA2C and DA2D, they need not be same. Okay. So, that way there will be some delay associated with the wire. Then there are some functional delay models. So, for so it is for more complicated functional elements like flip flops, etc. So, it may so happen that for going for one output state to another output state, it takes a different amount of time. For example, so if D and clock both are so if these are do not care, this preset line is preset bar is made high to low, then Q output will be becoming 0. So, Q outputs q present value of q is 0, then the output of q will go from 0 to high, low to high, and q bar will go from high to low. Now, delay in nanosecond to q is 1.6 nanosecond, to q is 1.6 nanosecond, and to q bar it is 1.8 nanosecond. Similarly, it may so happen that if you are asserting this clear bar line, then previous output was 1, now it becomes 0 in q and 1 in q bar, and these are the corresponding delays. So, asynchronous preset and asynchronous clear, they have got this type of delays. Whereas, for a normal operation, when this D line is 1 and there is a clock signal going up, the clock edge comes, then if the present bit is 0, it takes 2 nanosecond for q bar, for q output to change from 0 to 1, and 3 nanosecond for q bar. So, that way q 0 to 1 transition, it takes 2 nanosecond for q line and 3 nanosecond for q bar line, and this one 0 to 1 to 0 transition of q line. So, it takes 3 nanosecond and it takes 2 nanosecond for the q bar line. So, that way if we have got more and more complex logic modules, so there we can have different types of delays associated with different paths in the circuit. Next, we will look into this logic simulation. So, logic simulation, the first approach is the compiled code simulation. So, what it does is that it translates the logic network into a series of machine instructions that model the gate functions and interconnections. In fact, in the circuit, what we have is basically we have got the logic elements like AND gate, OR gate, NAND gate, NOR gate, etc. And if you look into any processor, then this processor normally has this type of statements. In their logic statements, we have got those things. Now, also if it is slightly more complex, like if it is a flip flop, etc., so that can also be modeled by means of some if then else statement, by by checking some signal values and all that. So, it can be converted into a piece of code. So, any circuit that we have, so we can convert it into a piece of code that we can execute on the host computer. Now, the way this compiled code simulation will work is that it will take the next vector. So, if the next vector is existing, then it will read the next input vector from the file. So, in a file the test vectors may be there. So, it take the next text vector v from the file, and it will run the compiled code with the input v in the host machine. So, it will v is taken as input, and with that the code will run, and whatever be the output of the program, that is the simulation result. Then again it will take the next input, next test vector, and again do the same thing till all the vectors have been simulated. So, this is possible because most of the machines they have got instructions similar to the logic gates and elements that we have. So, in a flow graph, it is like this: the gate level description, it goes through logic optimization, it generates then there is a logic levelization. So, logic levelization is actually telling us like like which gate should be or simulated at which point of time. After that, we have got code generation, and that gives us the compiled code. So, logic optimization is like this. So, maybe before optimization we have got a situation like this. So, there is a 3 input AND gate, out of that 1 input is permanently 1. So, that can be simplified to have a 2 input AND gate, where this only 2 inputs are there. So, for the simulation purpose, so I do not need to simulate the first one. Simulating 2 input AND gate is definitely simpler than simulating 3 input AND gate. So, that way it can be done. Similarly, there may be a NAND gate with only 1 input. So, that can be converted into an inverter. We can have one NOR gate where 1 input is permanently 1. So, we can convert it to a line 0. Similarly, there may be 3 inverters in a series. So, that can be converted to 1 inverter. Similarly, a buffer can be converted to a single line. So, this type of optimizations can be done, because for functional simulation, so we do not need to consider this type of we do not need to consider the situations that we have shown on the left hand side. Next part is to do a levelization. So, the objective of this stage is to determine the order in which the gate evaluations will take place. the problem is that if we have some logic circuit say like this, and so it has got a number of inputs and a number of outputs. Now, if I am trying to simulate this logic circuit, and all on a sudden I start I want to check what is the output of this AND gate. So, that is not possible because these values are still unknown. So, if I do a simulation here, I will get an u at this point. So, that most of the values will remain as u. But since these primary inputs are there, so the test vector that we have, so that has specified what are the values of these primary inputs. So, if I have a gate here which is fed from these primary inputs only, then I can simulate this gate first. Now, after that, if this gate feeds another gate like this, then I can simulate this gate. So, there is an order in which I should do the simulation. So, I should first simulate this gate, then this gate, and then level by level we should proceed. So, this is actually the known as a topological ordering of gates or topological ordering of nodes in the circuit. So, we can do it like this. We can have a very simple algorithm that can assign this type of levels. So, assign level 0 to all primary inputs, and we put all primary input fan out gates in a queue. Okay. If the so, now if the queue is not empty, then we pick up the next queue next gate G from queue. So, since this this gate G, since its inputs are all coming from the primary inputs only, so this must have been so their values are known. So, we can assign some level to this. So, is it ready to levelize? So, because it is we can, because all the inputs are known to it. So, I put this L to be equal to maximum of G's driving gate level. So, whatever be the levels of its previous previous inputs or the levels of its inputs. So, from them whatever has the maximum level, with that one has to be incremented, and that has to be assigned as the level of G. So, what we essentially mean is that say if I apply this algorithm onto this process, then for first this gate will be picked up, and these are actually leveled with zeros. So, this since these are primary inputs, so they are at level 0. Now, for this gate I know that all its inputs are at level 0. So, it will be leveled as 1, because as that 0 plus 1, that is 1. Now, when you are trying to levelize this node, then what will happen? So, there actually it has got two inputs, one of them has got a level 1, another one has got a level 0. So, we take the maximum of these two, that is equal to 1 and plus 1. So, 2. So, 2 is made the level of this OR gate. So, this way this leveling is done. So, any point of time when it is ready to level G, so we know that the node's inputs are already leveled. So, this we can now find out the level for this node. If it is not, then we just keep the node in the queue. So, later on it will be added. Now, this process continues till this queue becomes empty. If the queue becomes empty, means all nodes have been leveled. So, we have got the complete levelization of the nodes. Now, suppose say this node, this graph. So, in the first step, this A, B and C, so they are assigned level 0, and in the queue I have got these two nodes G2 and G1, because they are inputs, they are at the fan out of this A, B and C. Then at step 1, so I have got this 0, 0, 0. So, this A, B, C, so they all these nodes are there, and this G1, G2 remains. Now, G1 will be picked up. So, if G1 is picked up, then at the next level, so G1 will be assigned the level 1, and G1's fan out is G2 and G3. So, G2 is already there. So, G3 will be picked up. So, you see that here G2 was there in the queue, and since G2 is listed earlier in the queue, so it might have so happened that G2 is picked up before G1 for leveling. But when we pick up G2, we find that it has got some node G1 which is not yet leveled. So, G2 will be put back onto the queue. It is appended at the end of the queue. So, G1 comes to the top of the queue. So, in the next iteration, G1 is picked up, and then G1 gets leveled. So, that way it operates. The algorithm that we have noted there. So, if you follow the algorithm thoroughly, then you will find that at step number 5, all the gates will get leveled, and we will have the levels like 1, 2, 2, and 3. So, the orders that are produced, one possibility is that G1, G2, G3, G4, since G2 and G3 both have level 2. So, they can be done in any order. It may be G1, G2, G3, G4 or G1, G3, G2, G4, that does not matter. And in fact, if you look into this circuit, so this G2 and G3 they are not dependent on each other. So, they can be simulated in either order. Now, for the code generation part, so high level programming language source code may be used, like we can write down this piece of circuit, the code corresponding to the piece of circuit into some high level programming language. The advantage is that it will be easier to debug. It can be ported to any other target machine that has the particular compiler. However, limited in applications due to long compilation time. So, maybe it will take quite some time to do the compilation. So, that way it may be restricted. Other possibility is that we do it in the machine code directly. So, we generate the target machine code directly. So, in that case the simulation becomes efficient, because now we are not depending on any intermediate compiler. So, we know that if there is an AND gate, so we have to use the AND instruction of the processor. So, we can do this we can generate this target code directly, that is not very difficult in fact. So, that can be done. So, simulation efficiency will be better, but it is not that much portable, because if my system on which I am running this simulator, so if it has got say one particular processor, so if I take it to some other machine, then other computer, then it may not have that processor. As a result, the same code may not run there. So, portability becomes a problem, whereas high level programs they have the portability. Other possibility is to have interpreted code. So, interpreted code like say languages that has got interpreter in them. So, the target machine is a software emulator. So, it is the codes are interpreted and executed one at a time. So, this is we know that the AND gate, OR gate, NAND gate, NOR gate, etc. So, I can have the corresponding procedures written in that in the machine instructions of that target processor, so that it can emulate the behavior of these individual gates, okay, individual logic gates and flip flops, etc. So, that can be that way it becomes a software emulator, and the codes are interpreted and executed one at a time. So, this is best for portability and maintainability, because on the if you are taking on to some other system, so what you have to do is you just need to have the corresponding procedures written. So, in that system how this AND or NAND NOR are implemented. So, that particular interpreter, if it is written properly, then it will be working there also. So, these interpreted codes are better, but of course, performance will be slow, because interpreter runs slower than the compiled code. Another way of doing is the event driven simulation. So, event driven simulation means that if when some event occurs, then we will simulate the behavior, and we do not simulate the entire circuit. So, we simulate only the portion that is related to the event. So, here actually the example, like if we have got say this situation where previously we had the input 0, 0 and 1. So, this H, so 0, 0, 1, so this E was equal to 1. As a result, this G2 output H was equal to 0, this was 0, and this K output was equal to 1. Now, suppose there is event. So, event in the sense that some of the inputs do change, say A changes to 1 and B changes to 1. So, first this gate, since there is an event and say G1's input has changed. So, G1 will be simulated. So, G1 is simulated, and we see that this E value remains unaltered. So, if E value remains unaltered, that means wherever it goes, so that need not be simulated. So, this E value comes to G3, since G3 does not have any other input. So, G3 need not be simulated again, but this G2, it has got two lines in it, A and E. Out of that, E does not create any event, but this A creates an event. So, this node G2 has to be resimulated. So, this is simulated, and as a result H becomes 0 or 1, H becomes equal to 1 from its value of 0. So, there is an event on the line H. So, for the gate G4 again there is an event on line H. So, this gate has to be simulated and ultimately this is simulated and k becomes equal to 0. So, what we essentially show here is that there may be a portion of the circuit that need not be simulated when we are going in this event driven fashion. Like in this case, the gate G3 need not be simulated because its input is not changing. So, this is a very small circuit. So, there we see that a very small portion can be left out from simulation, but if we have got more complex circuits, then naturally this simulation it may be able to get rid of a larger portion of code from simulation or larger portion of the circuitry from simulation. So, that is the event driven simulation. So, this is often used to speed up the simulation process because we do not need to simulate each and every gate in the circuit. Now, there are the question of delay, like if it may so happen that these gates have got delays and these delays are to be taken care of. Okay. So, if there is a 0 delay, if we assume that the gates with events at their inputs are they whenever some event occurs at the input, immediately the output will be computed. So, in this case it is simple because we do not have to wait for anything. So, the flow chart may be like this: we start, read the initial condition. If that initial after the initial condition has been read, then we check whether there is any test vector pending. If a test vector is pending, we read the next input vector, put active primary inputs fan out gates in queue. So, primary inputs are modified after reading this input vector. So, whichever primary inputs have changed, so their fan out gates are put into queue. Now, we need to simulate those gates only. So, we again do the same thing, that all those gates fan out, all those put G's fan out gates in queue. Suppose we have taken the gate G. So, that for simulation, so that gate will be that gate's fan out nodes will be put into queue. Again, if the sorry. So, this is coming here. If the if it is put into queue. So, now it checks whether the queue is empty or not. If queue is not empty, then it will evaluate the next gate G from queue, and if it is equal to, if it is correct, if it is evaluated, then if the output changes, then only it will be the fan out nodes of G will be put into queue. If output does not change, then the fan out nodes are not put. So, that is basically that event driven portion, and you see that there is we have not considered any delay. So, as soon as G's input changes, so we are evaluating it to see whether its output is going to change or not. So, that is why it is a 0 delay event driven simulation. Ultimately, queue becomes empty when we have simulated all the gates using this event driven policy for the particular test vector, and when it is over, then it will check the next vector, and if it will take up the next vector, try to simulate it, and finally, when all the test vectors are over, it will come to the simulation will end and it will come to an end. So, we will continue in the next class.